The group members are Jiaying, Yishen, and Chen Feng. The agenda for this presentation will be the problem statement, challenges faced throughout the project, data preprocessing, and elaboration on the machine learning models used, comparing the results of the model, and lastly, conclusion to wrap up. Firstly, the problem statement. It is difficult to classify the species of crop seedlings. As such, we will be experimenting different approaches and observing the results to construct a model with the highest classification accuracy that solves the stated problem. Many challenges were faced by us throughout the project. The original dataset provided by Kager was used initially to train a simple CNN model. However, the results obtained from Kager system shows an accuracy of only 35%, which is very low. The reasons for such low accuracy obtained could be due to, firstly, dataset consisting of many noises. To reduce the noise within each image, pre-processing was done before the images were trained in each model. In this experiment, we proposed the use of certain classes from a popular images processing library, OpenCV, to assist us with the processing of images. Gaussian blur, HSV converter, mask, and Boolean masking are examples of classes that will be used. Each class will be explained in detail in the later part of the presentation. Second reason could be the imbalanced dataset. Likelihood of machine learning models learning in favor of classes with higher dependency increases when there is an imbalanced dataset. To reduce the chances of models training bias toward classes with higher dependency, we took the following approach. Firstly, we split the training and valid in a ratio of 9:1 instead of the usual ratio of 7:3. Next, we perform shifting of the dataset during the splitting of the dataset process. This approach will give more datasets for the models to train while decreasing the chances of models learning bias towards any individual classes in the dataset. Both challenges were solved with their respective solutions whereby experiments were able to produce an accuracy of more than 25% in a Kager system. Next, I'll be explaining about the data preprocessing that we have done. The trained dataset obtained from Kager contains 4,750 images from 12 different classes, while the test dataset contains 794 images to be classified. In any machine learning problem, a skewed data distribution can naturally occur due to the nature of the data, such as the data found in disease diagnosis and fraud detection. In such cases, one class can dominate the others. Jabkovic studied the effects of imbalanced data by generating imbalanced datasets synthetically, and the results showed that sensitivity to imbalanced data increases as the problem complexity increases. Therefore, we have to examine our dataset to observe whether the data distribution is highly skewed. As shown in the figure, there are no two or more classes with high discrepancy. The class with the least data has 221 samples, while the class with the most data has 654 samples. The ratio of the least sample class to the most sample class is approximately 1:3. Hence, all available trained data will be used for training the model. As seen from the figure, we can observe the background noises and lighting which are undesired and could potentially affect the model during the training process. In order to reduce the noise level, we applied the Gaussian blur filter with kernel size of 5x5. The Gaussian filter smoothens the edges by blurring the details. This results in a reduced level of background noises. After reducing the background noise, the background can be removed and only the main object in the image will be retained. First, the color space of the image is converted from RGB to HSV. RGB color space describes colors in terms of the amount of the red, green, and blue present, while the HSV uses hue, saturation, and value. The HSV color space allows the image luminance to be separated from the color information. This effectively improves the robustness when dealing with images from different lighting conditions. The figure shows a sample training data that has been converted from RGB to HSV color space. With HSV color space, objects can be segmented based on its color. Since the crop seedlings are of the similar color, an upper bound value and a lower bound value can be defined as the thresholds to segment the main crop seedling object. The threshold values are determined by sampling from the data set from all 12 classes. With the segmentation of the crop seedling object, a kernel or mask that covers the background can be constructed using morphological transformation. The figure shows a sample of a segmented crop seedling with masked background on HSV color space. Then, the same kernel is applied on the original image to segment the crop seedling object. As seen from the figure, the background noise is completely eliminated, while the crop seedling object is retained, ready to be used for training the classification model. Moving on, I'll be elaborating more about the machine learning models used. The convolutional neural network, aka CNN, is a specialized feed-forward neural network that was designed to process multidimensional data such as image data. In general, a CNN model consists of convolutional and pooling layers along with fully connected layers. Each convolutional and pooling layer are grouped together into a module. One or more convolutional modules can be stacked together with one or more fully connected layers to form a deep model. The convolutional layers act as filters for images, which extract and learn the feature representations of the input images. They are also used for calculating the matched feature points during the testing phase. The outputs of the convolutional layers are passed to the pooling layers, whose objective is to string the large size of image while preserving the most important information. This is achieved by selecting the maximum value in the window, which represents the best fit of the spatial features. In order to stabilize the model and speed up the training time, batch normalization layers are added to the CNN model. Batch normalization standardizes the mean and variance of each unit, hence normalizes the inputs to the layer. This helps in reducing the model network sensitivity to weight initialization. To prevent overfitting, dropout layers are added to the CNN model as a regularization method. A dropout unit is hidden from the network temporarily, including its incoming and outgoing connections. During training, the units are retained at a predefined probability P. By making the presence of other units unreliable, a unit must take the responsibility to perform well in different contexts, which improves the generalization of the unit. Transfer learning is a technique whereby a model that has been trained on one problem can be reused to solve another similar problem. We'll be experimenting with three of the most popular ones, namely the VGG, Inception, and ResNet models. One of the most useful features that we can benefit from the pre-trained models is that they were trained on more than 1 million images for 1,000 categories. This means that the models have more or less mastered the way to detect generic features from images. Besides, these models have achieved the state-of-the-art performance as they have proven to be the most effective models on a specific image recognition task. Moreover, these models are publicly available and can be easily accessible. Many libraries including TensorFlow and PyTorch provide APIs to download the model weights for convenient transfer learning use. In this project, VGG16, VGG19, Inception V3, ResNet 50, ResNet 101, and ResNet 152 will be experimented. After the dataset is being pre-processed, the first part of the project was to train these pre-trained models using our customized dataset based on the original layers that is offered by the respective pre-trained models. After which, these models will be added to additional dense layers, batch normalization layers, and dropout layers to restart their individual training with the same dataset. Now moving on, comparing results obtained from the models. Observed from the figure, there is a trend in each different type of models whereby there will be slight improvement between models with and without additional dense layers and batch normalization layers. Although additional layers might hinder with the training time of each experimental model, it is still feasible to add optimal measures to improve the accuracy of each model, such as pre-trained ResNet 152 and pre-trained ResNet 152 with additional dense layer and batch normalization, where training times are relatively close to each other when training with Google Colab Tesla T4 GPU. Furthermore, an interesting observation can be made from the figure when comparing with the pre-trained models and the regular CNN model. Although the regular CNN model was able to attain a decent result, the pre-trained models such as the ResNet 50 model outperformed the regular CNN model in terms of valid accuracy. This could be due to the benefit of using a transfer learning approach where images of certain interest were trained before training our customized dataset, which in turn might improve our training speed and accuracy when training huge datasets. The figures below shows the result of the models obtained from Kaggle system. Similar to the results in the previous slides, we can achieve a slight improvement when adding additional dense layers and batch normalization to optimize the models to produce a better result. The Inception V3 with additional dense layers and batch normalization is the best model where we can achieve up to 94% accuracy from Kaggle system. Lastly, the conclusion to wrap up the project. In this project, we are tasked to investigate various models that are suitable for the selected machine learning problem as mentioned at the beginning of the presentation. Firstly, various OpenCV methods are explored to perform masking to crop out what is not needed for the training and testing. Next, CNN and other transfer learning approaches were explored and evaluated. Lastly, models will perform prediction and results will be sent to the Kaggle system for grading. Finally, Inception V3 with additional dense layers and batch normalization was able to achieve the best accuracy of 94% among the rest of the experimental models, which places us at the top 50% in the leaderboard. This is the end of our presentation. Thank you.